Yes, I'm dressed up today. I hope you're not watching this in your jammies. This is the final screencast on process synchronization. These are today's topics, and one last time, the chapter objectives. We'll take a look at these three problems to demonstrate how we use our newly discovered synchronization primitives. The bounded buffer problem is nothing new. We've seen it a couple of times already. Just as a review, we've been calling it producer consumer. We have n buffers buffering the production by the producer and the consumption by the consumer. We'll use a semaphore called mutex to control access to that shared buffer pool, and then a semaphore full to control the producer, and a semaphore empty to control the consumer. Actually, that's the other way around. Full is used by the consumer, empty is used by the producer. But the producer needs empty buffers, the consumer needs full buffers. So here's the code for the pseudocode for the producer process. Note that the first thing that the producer does is wait on empty. And remember, empty is initialized to n, the number of buffers. So that forces the producer to wait when there are no empty buffers. The mutex is actually used to control the critical section. So mutex is a binary semaphore, and empty here is a counting semaphore. What's not shown is the logic to copy data into the buffer and actually figure out which is the next empty buffer. But that's a detail that we don't particularly care about, since we're focused on the synchronization bits here. Something to think about is what the effect would be, if any, if the two weights are switched with each other. In other words, what would happen if the consumer performed the wait on the mutex, then followed by the wait on full? And I'll pause here for a moment so that you can think about that. Why don't you pause the screencast, think about it, and I'll tell you what happens in a moment. So what will happen if this consumer holds the mutex and then blocks because there are no full buffers? We now have a deadlock, because the producer, if it's ready to produce, it has to acquire the mutex, which it won't be able to do. So it'll be waiting forever on the mutex, while the consumer here is waiting forever on full. So here's the writer's problem. We have some number of processes that are just reading a set of shared data, and they can all read simultaneously because they're not modifying the data. There are no synchronization issues there. But we also have a separate set of processes that both read and write, and only one of the writers can be in its critical section at a time, and while the writer is writing, none of the readers should be reading. And then at the bottom we see the shared data. There's the actual data set, which is the data that's being read and written. A reader-writer mutex that's used to control access to the entire critical section, and then a mutex, which is used to control access to read count, which is an integer that keeps track of how many readers are reading at any time. So here's the structure of a writer. It's simple enough. It just waits to gain control of the reader-writer mutex, performs its writing, and then releases its mutex. What's not shown here is the remainder section. So presumably these writers aren't performing writing all the time. So here's the structure of a reader process. Let's imagine that there are no readers and no writers in the critical section, and we're a reader, and we're since there are no readers or writers in, we're going to be the first one in. So we perform a wait on the mutex. We'll acquire that immediately. We then bump up read count. Read count will now be 1. So since we're the first one in, we acquire the read write mutex on behalf of all the other readers, and then we release the mutex. So note that if another reader tries to follow in behind us immediately after we've acquired the mutex semaphore, that reader will wait there. So it won't be the case that we have two readers trying to acquire the read-write mutex. But as soon as we release the mutex and begin reading, the next reader in will acquire the mutex, increment the read count, but now it'll see the read count is a value greater than 1. So it won't try to perform the wait on the read write. So it's not necessarily, I wouldn't think of a specific reader as holding the read write mutex. The readers as a class hold that read write mutex, and that philosophy is reflected in the code that's executed when a reader is leaving the critical section. So similarly, the reader performs a wait on the mutex, decrements the count, and if it was the last remaining reader, it will signal the read-write mutex to signal that there are no readers or writers in the critical sections, and then it releases the mutex. So there are two versions of the readers-writers problem. In the first variation, readers have priority. In the second variation, writers have priority. And I'll ask you to think about this with regard to the solution that we just discussed, whether or not it's the first variation or the second variation. I'll pause, you think about that for a minute. So the code that we just went over is the first variation. The readers have priority. In that variation, the writers can starve. In the second variation, readers can starve. So we all know that all philosophers do is think and eat. And in the dining philosopher's problem, there's a shared bowl of rice in the middle of the table, and 5 philosophers and 5 chopsticks, 1 chopstick between each pair of philosophers. And in order to eat, when a philosopher wants to eat, he or she has to acquire 2 chopsticks, the one to the immediate left and the one to the immediate right. So in terms of the data, you can see that at the bottom. There's the rice represents the data set, and the chopsticks are represented by 5 binary semaphores. So here's the structure of the code for a philosopher. In essence, the philosopher acquires the chopstick to the left and the chopstick to the right. And we have a little bit of modulo arithmetic there to determine the next chopstick. So think about for a moment what the problem is with this algorithm. And here's a solution. Imagine that the code executes in such a way that every philosopher wants to eat at the same time, and they all acquire the chopstick to their left, which they'll be able to do, but then none of them will be able to acquire the chopstick to their right. So they're deadlocked, and they will all starve to death. And if you've never seen a process starve to death before, I can assure you it's not a pretty sight, nor does it smell all that well. So here are some solutions to that deadlock problem. I don't particularly care for the first one, allowing four philosophers to be sitting at the table simultaneously. Uh, the remaining solutions could result in the starvation of a particular philosopher. The second one uses a critical section to allow a philosopher to see if both chopsticks are available, and the asymmetric solution, which is fairly elegant mathematically, you assign a numbering to the chopsticks 0 through 4, and you require that the philosophers acquire the chopsticks in increasing numeric order. And that prevents a cycle from forming and will prevent deadlock from occurring. We'll see more about cycle elimination when we talk about deadlocks in a later chapter. So here are problems with semaphores. These first three result from the fact that semaphores are primitive, available to user programmers, and as we all know, programmers make mistakes from time to time. So the first one is a reversal of the signal and wait. Obviously, a wait should be performed on a mutex before it's signaled. The second one, replacing the signal with a wait. The process of waiting on the mutex twice will deadlock itself. And then finally, completely omitting a wait signal or both, which obviously will result in no synchronization whatsoever. And as we have seen already, deadlock and starvation are always an issue. Monitors are a solution to these problems with semaphores. Think of them as classes that have synchronization built in, i.e. Each class method is implemented automatically for us in such a way that only one method is running at any particular time during an object's lifetime. And in this schematic code below, the initialization code is of course analogous to a class's constructor code. So here's a diagram. Only one process is executing monitor code at a time, and the other processes are queued on what amounts to a semaphore. But the user of this monitor, a programmer using a monitor, doesn't have to write any synchronization code. It's taken care of by the compiler. As alluded to in an earlier slide, there are some synchronization situations that monitors can't handle on their own. So condition variables are a mechanism for handling such situations. For example, if we used a monitor to solve producer-consumer, and the producer is executing the produce method and suddenly discovers that there are no buffers empty, in some sense we don't want the producer to leave that method and leave the monitor. We want the producer to stay at that point in its method but block there. But monitors on their own have no mechanism to do so, and that's where condition variables come in. So a condition variable is best thought of as some Boolean condition that we test, and if true, it's tested typically in an if statement. If true, we just continue on. If the condition is false, then this wait call is executed. Um, that suspends the process but releases the mutex that's controlling access to the monitor as a whole. So the process waiting on a condition variable is suspended within the monitor. And then if the Boolean condition changes, signal is invoked by the process that has caused the Boolean condition to change, which will wake up a process waiting on the signal, or perhaps all the processes waiting on the signal. So this is a schematic view of a monitor with condition variables. So here are some of the design choices. So if P signals Q, does Q resume execution immediately, or does P continue executing, and once P leaves the monitor, Q is allowed to resume execution? Another design question would be if there are several processes that are waiting on a condition variable, and the signal on the condition variable occurs, does only the process on the head of the condition variable Q get released, or do all of the processes waiting on the condition variable get released? So here's a monitor solution to dining philosophers that uses condition variables. So for each of the 5 philosophers, they're either, each one is individually either thinking, hungry, or eating. Initially, they're all initialized to the thinking state, and then 5 condition variables upon which each individual philosopher will wait if it can't acquire the 2 chopsticks necessary for eating. Here in the pickup code, so this is what a philosopher executes if it wants to begin eating. It changes its state to hungry, executes the test method, which we'll see in a minute, checks to see, in essence, if the 2 chopsticks are available. And if they are, the test method itself changes the philosopher's state to eating. And then we see the actual Boolean condition. So if the philosopher is not eating, it waits on its condition variable. So the thing to notice here is that the condition variable itself is simply a suspension queue with wait and signal operations performed upon it, and the actual Boolean condition that is used with the condition variable is separate, right? This notion of is my state eating or not is not intrinsically bound to the condition variable self. And then when a philosopher is finished eating, it executes the put down method, which sets its state back to thinking, and then uses the test method to look to see if the philosopher to its left or to its right is now capable of eating, which either one of those may be, because chopsticks that they need are now necessary, or now available. So here's the code for test, and it's performing a rather important function. So imagine that we're trying to eat. So we're calling test, passing in our identifier. So in essence, we check to see if the chopstick to our left and the chopstick to our right is available. Hungry there, well, we know we're hungry. And if both chopsticks are available, we change our state to eating, which in the pickup code will allow us to proceed. And then signal it doesn't hurt to signals aren't remembered if no processes are waiting on the condition variable. If there's no process waiting, then the signal is simply thrown away. The other case is we're executing our put down method, and then we call test on the philosopher to our left and to our right. And you can see what we're doing on behalf of those philosophers is checking to see if they're actually hungry, and then whether the chopsticks each one needs are available or not. And if that is the case, we change that philosopher state to eating and then signal it so that it'll resume execution. So here's how each philosopher behaves. It executes the pickup method, eats, and then executes put down. And as noted, no deadlock is possible here because as one of the earlier solutions, well, this implements one of the earlier solutions of checking to see if both chopsticks are available before picking one up. But starvation is possible. It would be possible for two of the philosophers with a third philosopher in between them to conspire in such a way that that philosopher in between them starves to death. So let's look briefly at how monitors are implemented using semaphores. And again, remember that it's the compiler that takes care of this for us. We don't have to do it ourselves explicitly. So in addition to whatever class variables exist, the compiler will add these variables for, this is for global control. Mutex here is used to ensure that only one monitor method is executing at a time. And as we'll see, next here is used to suspend a process within the monitor for situations in which the process is not waiting on a specific condition variable. So the code for a procedure, a function or a method is acquire the mutex. And at that point, we know that we're the only process executing within the monitor. Execute the function's code, and then check to see if a process is suspended on next. And if that's the case, then signal next. Also note that that process that is signaled implicitly is gaining control of the mutex. Otherwise, if there is no process waiting on next, we simply release the mutex. For each condition variable, we implement that with a semaphore and a count of the number of processes that are waiting on the semaphore. You can see here the code on wait, increase the number of waiters. If next count is greater than 0, meaning that there is some process waiting to re-enter its method within the monitor, then signal that process. Otherwise, and remember that process that is being signaled out of next implicitly acquires the mutex. Otherwise, release the mutex and then wait ourselves on the semaphore associated with the condition variable. Here you can see next coming into play in the pseudocode for signal. So if we're signaling and there's a process waiting, we're going to put ourselves to sleep and pass control to that process that's waiting to get back into the monitor. So we increment next count, signal the X semaphore, the semaphore associated with the condition variable, and then block ourselves on next, which remember is a global semaphore. I'm going to skip this, which means I'll skip this and skip this. I'm going to skip over each of these examples, although I'll pause in each slide so that you can scan it if you so desire. So here's Solaris synchronization, Windows synchronization, Linux synchronization. Aren't you glad I'm reading these titles to you? Okay, you can read this title yourself. And that finishes chapter 5. What are you waiting for? A signal? Signal.